2.5 measures of position. So how can we understand the position of our data in the collection? Perfect. The first thing that you can work on with is quartiles. So quartiles denoted by Q, we usually have 3 quartiles to work with. First quartile, second quartile, and third quartile. They divide an ordered data. So first you have to put the data in order. Then it set your data into 4 equal parts. About 1/4 of the data fall on or below the first quartile. We denote the first quartile by Q sub 1. About 1/2 of the data fall on or below the second quartile, Q sub 2. About 3/4 of the data fall on or below the third quartile, which is denoted by Q sub 3. Okay, so suppose this is your collection. First of all, you have 3 quartiles, Q sub 1, Q sub 2, Q sub 3. I expect you to ask, so what is this end values? This is your minimum, and this is your maximum. Q sub 2 is always the median. Again, you have 3 quartiles, Q sub 1, Q sub 2, Q sub 3. The beginning value, the first value, is the minimum value, and the data stops at maximum value. Remember the definition of median? Median is measure of center, which is in the middle of your data. Q sub 2 for second quartile is always the median. Example, suppose you have a collection of data and you're interested in finding the quartiles of your data. Okay, perfect. Here we have the number of nuclear power plants in the top 15 nuclear power producing countries in the world, which are listed here. So you have 15 numbers in your collection. As you can see, they are not in order. So you have 7, you have 20, you have 16, you have 6, 58, 9. Okay, so they are not in order, not written in order. Let us get back to the definition. The 3 quartiles, Q sub 1, Q sub 2, Q sub 3, divide an ordered data. So first, you have to write this data in order from smallest to largest. Okay. Take a look at this. The smallest value is 6. Then you have 7. Then you have 8, 9, 10. After 10, we only have 15. Then it comes 16. We have another 16 to 16 in your data. Then you don't have any 17, you don't have any 18, you don't have any 19, but you have 2 20s in your collection. Then you have 23, 33, 50, 58, and 104. It seems like 104 is an outlier. So the minimum value in your collection is 6. the maximum value in your collection is 104. First, you find the median. Find the median of your collection. Since you have 15 entries in your collection and 15 is odd, it means that the middle value is going to be the median. So since 15 is odd, the median is the middle value. So 7 from left, 7 from right, the middle value is 16. Median or second quartile is 16. We found the second quartile first. So as you can see, your data is divided into two pieces, two collections. One collection on the left, one collection on the right. Again, you calculate the median of these two collections. The median of the first collection, how many numbers do you have? 1, 2, 3, 4, 5, 6, 7 is going to be the middle number. So the median of the first set is your first quartile. So the median of the first set is 9 or Q sub 1. Okay, now forget about your first set. Forget about your first collection. The second collection on the right-hand side of Q sub 2 has 1, 2, 3, 4, 5, 6, 7 numbers in it. The median of the second collection is 33. So the third quartile is nothing but the median of the second set. The median of the second set is 33 for Q sub 3. Okay. Please take your time if you want to take note. 15 is an odd number. 14 is even, 16 is even, 17 is odd, and so on. We have even numbers, we have odd numbers. Any question here? Any confusion? Since you had 15 numbers in the collection, to find the median, you separate these from left, from right, 7 numbers on the left, 7 numbers on the right-hand side, and the middle value is going to be the median or second quartile. Guys, any question here?
Professor, I have a question. So
Go
the
ahead.
number set you shows have an odd number. What if we have like an even number set, like data
So
set?
then let me write this for you here. If you have even numbers of collection, number of data in your collection, note. So suppose you had 6, 7, 8, 9, 10, 15, 16, another 16, 20, 20, 23, 33, 50, and 58. I'm just eliminating the last number. Now I have 14 data in my collection. Guys, this is a note if you have even numbers of entry in your collection. Now we have 14 entries in our collection. 14 numbers. Okay, first we find the median of the original collection. Very well. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The middle numbers are these two numbers. Okay, 16 plus 16 divided by 2 is 16. So 16, or the middle number here, is your second quartile or the median. So Q sub 2 or the middle number is 16. Any questions so far?
So would both of the 16s be quartile 2?
So not both of them, the middle number, which is invisible in this case. The middle number, the invisible middle number is 16, dividing this set into two collections. First collection on the left, second collection on the right.
Okay.
Now you have to find the median of each of these sets. Okay, the first set has 1, 2, 3, 4, 5, 6, 7 numbers. We're lucky, it's odd. So the middle number is your first quartile. Now you look at the second set. 1, 2, 3, 4, 5, 6, 7. We expect to have 7 numbers because we divide this into two equal sets. The middle number, 23, is the median of the second set, and we call it the third quartile. Any other question? Make sense for everyone?
Yeah, it makes sense. Thank you.
Perfect. Sure, definitely. Okay, let us move on to next page. You need a minute to finish writing this. Okay, let us move on to the next page. Okay, now what if we have a lot of numbers? Of course, we're interested in using our calculator. Okay, to find quartiles, it's exactly the same as finding the mean, standard deviation, and statistics for your collection. What are you going to do? You're going to use your calculator. First, you have to enter the data. So first you go to stat, then go to edit, enter the data in L1, L2, then you go to stat again, you go to calc, one variable, enter, enter, enter. Then it gives you your mean, It gives you your standard deviation. Your standard deviation is either for the sample S of X or sigma X, which is for population. Then if you go further down, you see Q sub 1, the first quartile, the median, which is Q sub 2, and third quartile. It also gives you the minimum, the maximum, and so on. By using a calculator, you can see the first quartile, the second quartile, and the third quartile for this collection are going to be these numbers. Please take your time, work with your calculators. Feel comfortable using your calculator. So your TI-84 will give you one variable stats, n equals to 25. It means that you have 25 numbers in your collection. If you count these numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Minimum value is 19. Maximum value is 46. Median or second quartile is 32. First quartile or the median of the first collection is 26.5. And Q sub 3 or the median of the last collection, second collection, is 40.5. Move on to next page. Any question about your calculator? Here's a definition for you. Interquartile range. The interquartile range is actually the difference between your third quartile and first quartile. Interquartile range, Q sub 3 minus Q sub 1. Third quartile minus first quartile. We call it interquartile range, and we usually denote it by IQR. Why we need that? We usually use interquartile range to find outliers in our collection. How do we do that? We have to follow some guidelines. First step, find first quartile, then find third quartile, then do the subtraction between third quartile and first quartile, subtract first quartile from third quartile, interquartile range, then after finding this number, multiply that by 1.5. Then you need to find this number here, which is Q sub 1, first quartile, minus the number that you found in the third step. It gives you a number. After doing the algebra, you have a number. Any number less than this number is going to be an outlier. In the last step, you add the third quartile and the number that you found in the third step. Any number greater than this number is going to be an outlier. So, any number in the collection less than less than. There is no equality. Q1 minus 1.5 times interquartile range is an outlier. Any number greater than Q sub 3 plus 1.5 times interquartile range is going to be an outlier. This is the guidelines that you have to follow to find possible outliers in your collection. Please take your time, take note, then we go over one example together. Very well. Okay, let's see what's going on in one example to feel more comfortable about this guideline. Okay, using interquartile range to identify an outlier, we're getting back to example 1. So let us take a look at example 1. What we learned in example 1. In example 1, we learned that we have a collection of data, and what was our goal? Our goal was to find first quartile, second quartile, and third quartile. Okay. 9, 16, and 33 are the numbers that we're going to work with. Q1, 9, Q2, 16, and Q3, 33. Very well. So step 1 says find Q1 and Q3. So as you can see, we don't need the second quartile here. In step 2, we need to find interquartile range. Q3 minus Q1. 33 minus 9, which is 20. Then in step 3, multiply interquartile range by 1.5. 1.5 times 24, which is a number. So if you do the calculation, you get 36. Then it says calculate Q1 minus the number that you found by multiplying interquartile range and 1.5, which is 36. So Q1 is 9 minus 36 gives you negative 27. Okay, let us stop here. Let us get back to our example 1. Do we have any negative numbers in our collection? Take a look at your numbers. Do we have any negative numbers here? All numbers are positive. Since we don't have any negative number here, it means that negative 27 doesn't give us any information about any possible outlier. Okay, perfect. So here you can say, since all numbers are positive, negative 27 does not give us any information. So it means that we couldn't get any information by this calculation. Last step, add Q3 and the number that you found by multiplying 1.5 and 24. Q3 plus 36. What was my Q3? My Q3 was 33. 33 plus 36 is 69. If I have any number greater than 69 in my collection, that number is an outlier. Okay, let us get back to our collection. Do we have any number greater than 69 here? Yes, of course. I see 104 in my collection, which is greater than 69. So 104 is an outlier. For sure, you can say that 104 is an outlier. Since 104 is greater than 69, so 104 is an outlier. Any question? Any confusion here? Please take your time, take notes. Let us move on. So how do we visualize the data when you want to use first quartile, second quartile, and third quartile? It means that when do we use quartiles and how do we visualize data using quartiles, especially when you have outliers? Very well. It's super easy to form a box and whisker plot. First, you have to find the minimum value in your collection. Then you find your first quartile, you find second quartile or the median, then you find the third quartile, and finally, you identify your maximum data in the collection. Remember that we call these 5 numbers as a 5-number summary. Perfect. So, on the far left, you start by locating your minimum value in the collection. On the far right, you locate your maximum value. Then you have 1, 2, 3 vertical line segments. The first vertical line segment is for your first quartile. The second vertical line segment is for your second quartile or median. And the last vertical line segment is for your third quartile or Q sub 3. Then you connect these together to form a rectangular box, rectangular shape, and you connect the minimum entry, the maximum entry to form your whiskers. The center of your data is the median, the typical value, or the center or balancing point. Center or balance is your median or second quartile. Please take your time. Guys, take a look at this Super Bowl attendance on the left-hand side. We have a box Whisker Plot. As you can see, here you have 62 as the minimum value, 104 as the maximum value. The center or the balancing point or the median is 75. So if you want to graph this, the graph is going to be like this, the graph of the data. It's highly skewed to the right-hand side, skewed. Why is that? Because my typical value is here, 75, and I have a number 104, which is far away from the center. So you have a skewed graph. That's the main point of using a box and Whisker plot, especially when you have outliers. You can easily identify the outlier. Let us take a look at this example. Example 4, draw a box and Whisker plot for your data in example 1. So in example 1, let's get back to example 1. Let's see what do we have here. We have a collection of data. So the minimum value is 6. The maximum value is 104. We need to identify 5 number summary. 9, 16, 33. So 6, the minimum value, maximum value 104, first quartile, second quartile, and third quartile. So we identify 5 number summary for the data. Then, okay, the minimum value is 6. The maximum value is 104, first quartile, second quartile, third quartile. As you can see, we have vertical line segments to identify those quartiles because we want to form a box to show that the majority of the data are located here. Perfect. So as usual, if you want to graph this collection, the graph is going to be like this, highly skewed to the right-hand side. The tail is on the right-hand side, so it is skewed to the right. Tail on the right, skewed to the right. So let us read the interpretation together. The box represents about half of the data, which means about 50% of the data entries are between 9 and 33. You can actually see that. The left whisker represents about 1/4 of the data, or about 20% of the collection are less than 9. The right whisker represents about 1/4 of the data, so about 25% of the collection are greater than 33. So 25%, 25%, the rest 50% are here.
So that would be with the every data, right? The left whisker would be 25.
Exactly, exactly.
Okay.
Remember the definition of first quartile, second quartile, and third quartile?
Yeah, I got it.
Perfect. Very well. So other than quartiles, we have, for example, percentiles. Percentiles are very important. Percentiles divide a data set into 100 equal parts. Percentiles. You've seen percentiles many times, especially when it comes to scores, SAT scores. For example, take a look at example 5, interpreting percentiles. So suppose you have the data collection, and here you have your scores, and here on the vertical axis, you have your percentiles. Perfect. From smallest to largest scores are all located on the horizontal axis. On the vertical axis, you have the percentiles. Okay, what's the meaning of that? So let us take a look at the lowest numbers here. 600, 700, 800, 900, okay, 1,000, 1,200, and so on. So take a look at the middle number. The middle number, okay, is something like 1,600, and on the vertical axis, if you match it with the vertical axis, you see roughly 60th percentile. It's very close to 60th than 70th. So what's the meaning of that? It means that almost 60% of the students who participated in SAT exam got lower than 1,600 on their exam. So about 60% of the students, 60% of students who participated in the exam got lower than 1,600. So suppose you had 1,000 students participated in a SAT exam. %60 of them, 60% of 1,000 students, which is 600. 600 students got lower than 1,600 on the SAT exam. It means that only 40% of the students, or 400 students, got above 1,600. Okay, so this is how we read a graph. But how do we actually calculate the percentile? To calculate the percentile, first we write the data in order. Guys, put the data in order, then count the number of data entries less than X divided by the total count. How many data do you have in your collection? Do the division, multiply it by 100, and round it to the nearest whole number to find the percentile of the number that you have. Reading the graph and actually doing algebra to calculate the percentile of a number. A quick example. Think about our first quiz. First quiz. Okay, suppose I had the collection, I took a sample of my data on my collection, and I have these grades. I have 8, 8, 8, 9, 9, 9, 9, 10, 10, 10, and 10. So this is a sample from my class. This is a sample. I want to know how many percent of students got lower than 10. So I want to know what's the percentile of 10. Lower than 10. Lower than 10. This is a random sample. Percent of students who got lower than 10. So I have to follow the formula. This formula says I have something on the numerator, I have something on the denominator. On the numerator, I count the number of data less than 10. Do I have data in order? Yes. So how many numbers are less than 10? 1, 2, 3, 4, 5, 6, and 7. So 7 goes on the numerator. How many data do I have in total? 8, 9, 10, 11, 12. 12. Then after doing the division, I'll multiply this guy by 100. Please calculate this number. What is 700 divided by 12? What's your percentile? 58%? Thank you, guys. So it means that 58% of the students got lower than 10. It means that 42% of the data of the students are above 10. You get the big picture? Make sense for everyone? Very well. Let us take a look at another example. So here you have example 2, and your goal is to find the percentile that corresponds to $30,000. First, we put the data in order. 19, 22, 23, 23, 26, 26, 27, 27, 27. Guys, repetition is important. You have to list all the numbers, then 30, 31, 32, and so on. The percentile of 30 is the number of data less than 30. So we have to count 1, 2, 3, 4, 5, 6, 7, 8, and 9. I have 9 numbers less than 30. So 9 goes on the numerator. How many data do I have in total? Total, how many? Okay. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and 25 goes on the denominator. Then I multiply the outcome by 100 and I get 36%. So 36% of the data are below 30. Let us continue. The most important measure of position is z-score or standard score. We're going to see this guy for the rest of the contents in the rest of the materials, and z-value, z-score is very important. Very well. To find z-value, you have to have your mean and standard deviation. The z-value corresponds to x, is x minus mean divided by standard deviation. What does it do? It actually rescale your data. Standard score or z-score represent the number of standard deviations. A value like x lies from the mean mu. Okay, so suppose this is your original collection, and suppose you have a normal distribution. This is your mean. This is mean plus 1 standard deviation. This is mean plus 2 standard deviation. And this is mean plus 3 standard deviation. On the left-hand side, mean minus 1 standard deviation, mean minus 2 standard deviation, and finally mean minus 3 standard deviation. Okay, this is your mean in the middle of the data. Okay, suppose your x is here. This is your x. This is just a random number in your collection. We can use z-score to convert the original data into a normal distribution with mean equal to 0, mean equal to 0, mean plus 1 standard deviation, 1, mean plus 2 standard deviation, 2, mean plus 3 standard deviation, 3. On the left-hand side, -1, -2, -3. Now your x is converted into z. Remember that we say that any data above 2 standard deviations away from the mean is unusual. 3 standard deviations away from the mean is highly unusual. A z-value outside the range of 2 standard deviation is considered unusual, and 3 standard deviations above the mean or below the mean is considered as highly unusual, very unusual. So take a look at this shape. As long as that number is near the mean 0, near the mean 0, it means that you have a usual value. It is located 2 standard deviations or 3 standard deviations away from the mean. You consider it as unusual or highly unusual value. Perfect. Example. Our goal is to find z-score and decide if we have unusual or highly unusual data or value. Okay, first of all, we have to identify keywords. The mean is equal to 56. So quickly write mean is 56. Then another keyword, standard deviation, is 4. So standard deviation is equal to 4. Then your goal is to measure the speeds of 3 cars traveling along this stretch of highway as 62. So my first car, my first X is 62. Let us find Z value for X equals to 62. So we know that Z is X minus mean. We have a formula. We memorize this formula divided by standard deviation. So Z of 62 is 62 minus mean divided by standard deviation. If you do the calculation, you have 1.5. Is it greater than 2? Is it greater than 3? No, so it's not unusual. 1.5 is not greater than 2, so it is not unusual. That makes sense. The speed is 62, which is very close to the mean, so we're good. We're not worried about 62. The next one, 46. My next X is 47. So my goal is to check to see if it's unusual or not. What is its Z? We have to do the calculation. X minus mean is 56, divided by standard deviation. If you do the calculation, you have a negative number, negative 2.25. Is it less than negative 2? Of course. So if you look at the horizontal axis, when it comes to Z-score, the mean is 0. The mean is always 0. First, 1 standard deviation, 2 standard deviations, 3 standard deviations, 1 standard deviation below, 2 standard deviations below, 3 standard deviations below. Okay, negative 2.25 is going to be here. As you can see, it is less than 2 standard deviations away from the mean, so this speed is unusual. And finally, so this is 447. The last one is 56. 56 is the same as my mean. It means that the driver is a good driver, driving the same speed as specified, 56. So if X is 56, your Z is 56 minus 56 divided by standard deviation, which is 4. 0 divided by 4 is 0. And this is just here. And this is for 62. It's not unusual. Okay, we have a question in the chat. No question? Okay. Any question? Any confusion? So this is for the first driver, this is for the second driver, and this is for the last driver. Very well. Our last example. Here you have two populations. The first population is men's heights. The second population is women's height. Of course, we have different mean. We have different standard deviations for these populations. First population, second population. Okay, question says, compare z-scores for 6 foot tall man and a 6 foot tall woman. Of course, we have different populations. We get different z values. So your x is the same. So convert your x, which is 6 foot tall, into inches. Why is that? Because the unit in the population is in inches, not foot. Okay. Then we compare z-scores. The first z-value, 72 minus 69.9 divided by 3. My first z-value is 0.7. Very good. It's very close to the mean. The second z-value, 72 minus 64.3 divided by 2.6. The second z-value is 3. Oh God, that's a very unusual value. So take a look at these two z-scores on the horizontal axis. 0, 1, 2, 3, -1, -2, -3. The first z falls in the first standard deviation away from the mean, which is close to 1. We're not worried about that. For men, this is considered as a very acceptable height. But when it comes to population for women's heights, this is three standard deviations away from the mean, which is located here. So you say that the second value, your x equals to 72, is considered as unusual height for a woman. Very well. Take your time. If you want to take notes,